Hello. In the previous lecture, we started our discussion of the Bitcoin cryptocurrency. We now continue that discussion. So, we discussed last time that each block includes a block header and a list of transactions. We now discuss the structure of the block header. So, each block in the blockchain begins with a 80-byte block header, which is shown in this figure. So, the different fields of a block header are n version, then hash previous block, hash Merkle root, n time, n bits, and n nonce. We will discuss these different fields in this lecture and the next few lectures. And the sizes of different fields of the header are shown here. So, n version is 4 bytes, hash previous block is 32 bytes, and so on and so forth. So, this prefix n of the 4-byte fields, namely n version, n time, n bits, and n nonce. This prefix n indicates that they are integer variables. Similarly, the prefix hash of the 32-byte fields, namely hash previous block and hash Merkle root, this prefix indicates that they store hash function outputs. The n version field specifies the version of the block. We have discussed that there are different versions of the Bitcoin system. So, this n version stores the particular version of this block. As the Bitcoin system evolved, changes were proposed to fix bugs or to add new features. So, the version kept on changing each time. Hash previous block contains the double SHA-256 hash of the block header of the previous block in the blockchain. That is shown over here. So, this is the block header of a particular block, and the double SHA-256 hash of this header is computed, and that is stored in this hash previous block of the next block in the blockchain. So, recall that the blockchain is a linked list of several blocks. So, for a particular block, we find the double SHA-256 hash of the block header and store the value in the hash previous block field of the next block. By double SHA-256 hash, we mean the following. Let H denote SHA-256 hash. In that case, to find the double SHA-256 hash of a particular value x, we find h of x. So, that is it's another cryptographic hash function. So, we will see that throughout Bitcoin, as the cryptographic hash function, it uses double SHA-256. It's a measure to increase the randomness even further than computing the hash just once. Since the genesis block has no previous block, its hash previous block was set to all zeros. So, recall that genesis block is the very first block, and its hash previous block field was set to zeros because there was no block before it. So, next we discuss the hash Merkle root field, that is this one. So, that is also a cryptographic hash value. Hash Merkle root field stores the root hash of a Merkle tree that is formed using the transactions in the block. So, we will discuss the concept of a Merkle tree. So, this shows a Merkle tree. The transactions in the block are these T0, T1, T2, and T3. So, each of these transactions encodes the transfer of a certain number of bitcoins from a sender to a receiver. For example, T1 may record that Alice transfers 1 bitcoin to Bob. So, each of these is the transactions. We find the hash value of each of these transactions. So, H00 is the hash of T0, then H01 is the hash of T1, H10 is the hash of T2, and H11 is the hash of T3. And then we concatenate these two hashes H00 and H01 and find the hash of the resulting value. So, H0 is the hash of H00 concatenated with H01, and similarly H1 is hash of H10 concatenated with H11, and then we concatenate these two values H0 and H1, and the resulting value is H. So, these transactions are arranged so that they are the leaves of a binary tree. And then we keep on computing the values of the intermediate nodes of the binary tree. So the transactions are arranged as a list as shown here, and the double SHA-256 hash of each is computed. The hash function h here denotes a double SHA-256 hash. So each h here is a double SHA-256 hash. Using these hashes as leaves, a binary tree is created where each node is associated with a double SHA-256 hash of the concatenation of its child hashes. For example, we concatenate h0 and h1, and the hash of that is the double SHA-256 hash of that, is the hash of the parent of these two nodes. In this figure, the hash value h is the root hash of the Merkle tree. For a particular block, consider the transactions in the block. These are all placed such that they are the leaves of a binary tree, and then we keep on computing hashes in this manner. And when we get to the root of the tree, the hash value that we have computed for the root of this tree, that is the root hash of the Merkle tree, and that is the hash Merkle root field that is stored in the block header. So in the previous slide, we considered the case where the number of transactions in the block is a power of 2. So it is of the form 2 to the power n for some integer n, but that may not always be the case. So when the number of transactions is not a power of 2, then some nodes in the Merkle tree have only one child. So we see that in that case, this binary tree is not complete. So some of the nodes in this binary tree will have only one child. An example is shown here. In this case, the number of transactions is 3, so it's not a power of 2. This is the Merkle tree is shown here. These two transactions are concatenated and the hash is computed, and it is stored in this node. But what about this transaction? There isn't another transaction which can be concatenated with it. So in that case, the hash of the single child, such as this T2, is concatenated with itself and then hashed to derive the hash value associated with the parent. So we can see here that h10 is concatenated with itself, and we find out the hash of the concatenation of h10 with itself, and that is the value h1, which is stored in corresponding to this node in the Merkle tree. So this figure shows the case where there are 3 transactions. So this is an example where the number of transactions is not a power of 2. So what is the reason for using hash Merkle root field? So that is used for tamper resistance. If any one of the transactions in the block is modified, then once we compute the hash Merkle root field, that will not match the actual value. So any change to a transaction in a block will result in a change in the hash Merkle root field. So that prevents someone from modifying the one of the transactions in the block. A change in the hash Merkle root field in turn results in the change in the double SHA-256 hash of the block header. Recall that the hash previous block field of a block header contains the double SHA-256 hash of the block header of the previous block. We mentioned this during our discussion of hash previous block. So hence the hash previous block field of a block depends on all the transactions in all the previous blocks all the way up to the genesis block. So if any one of the transactions in the blockchain is changed, then the hash previous block field of all subsequent blocks will change. So that is the reason the blockchain has the property of tamper resistance. So we'll later see that this property is used for guaranteeing tamper resistance of the transaction data. So if we change any of the transactions in a block, then the hash Merkle root field will change, and hence the hash previous block fields of the next block as well as all following blocks will change. So why do we use a Merkle tree of the transactions for achieving tamper resistance? So here is an alternative simpler field that also achieves tamper resistance. So an alternative simpler field that could be included in the block header in place of the hash Merkle root field is the following. We could have just hashed the concatenation of all the transactions in a block and put the resulting hash value in the block header. For example, if the transactions in a block are T0, T1 up to Tn minus 1, then we could have just concatenated them to get T0, T1 and so on up to Tn minus 1 and found out the hash value of the result and store that in the block header. So this would also have guaranteed tamper resistance of the transaction data. So then why do we use such a complicated structure like Merkle tree? So Merkle tree achieves tamper resistance, but it also achieves one more important property. The reason for using the Merkle tree is the following. It enables efficient membership proofs of transactions within a block. So we'll discuss what this means. There are some nodes in the Bitcoin network called simple payment verification nodes. So earlier we discussed that there are different kinds of nodes in a Bitcoin network. One kind are full nodes which store the entire blocks. Another kind of nodes are simple payment verification or SPV nodes which store only the block headers and not the full blocks like full nodes. Suppose an SPV node Bob needs to verify whether a transaction say T1 involving Bob belongs to a block or not. For example, the transaction may say that Alice transferred X bitcoins to Bob. So hence Bob is concerned about whether the transaction T1 is there in the block or not. Bob has the header of the block but not the full block. So how does Bob verify efficiently whether the transaction T1 belongs to a particular block or not? Bob contacts a full node and the full node must efficiently convince Bob that the transaction T1 indeed belongs to the block. So by efficiently we mean that the full node must just send a small amount of data to Bob, but by examining this small amount of data, Bob must still be convinced that the transaction T1 indeed belongs to the block. How can the full node transfer such a small amount of data to Bob to convince him that the transaction T1 belongs to the block? So the full node sends a so-called Merkle branch to Bob to prove the existence of the transaction T1 in the block. So we'll discuss what is meant by a Merkle branch. It consists of certain of the hash values in a Merkle tree. So here's an example. Suppose we want to prove that the transaction T1 was involved in the calculation of the root hash h in the figure on the left. So h is the root hash of the Merkle tree, and we want to prove that the transaction T1 was involved in the calculation of this root hash h. So recall that the root hash of the Merkle tree is stored in the block header. So an SPV node such as Bob will have the block header and hence has the hash h. But we need to convince Bob that the transaction T1 was involved in the calculation of this root hash h. So what information must a full node transfer to Bob to convince him that T1 is involved in the calculation of this root hash h? So we only need to provide the Merkle branch consisting of these hashes which are highlighted in this figure on the right, namely h00 and h1. Now Bob knows the value of T1 and Bob has been provided this Merkle branch which consists of the hashes h00 and h1. Now let's see what Bob can do. Bob can compute the hash of T1, that is h01, and Bob has been provided h00, so he can concatenate h00 and h01 to get h0. So Bob can calculate h0, and Bob has been provided h1, so he can concatenate h0 and h1 and get h. So that tells Bob that this h can be generated in this manner using T1 as one of the inputs. So this way Bob is convinced that T1 is indeed involved in the computation of this hash h. So the hashes h01 which is here, then h0 which is this one, and h can be calculated from T1 and the Merkle branch consisting of h00 and h1 as we just discussed. So if the root hash h appears in the hash Merkle root field of a block header which Bob has, then we can be certain that this block contains the transaction T1. This is an example of efficient membership proof of transactions within a block. So in our example, the full node presented an efficient membership proof of the transaction T1 within a particular block, whose block header was present with Bob, but Bob did not have the full block with him. In general, the Merkle branch required to prove the existence of a transaction in a block containing n transactions has size O log of n to the base 2. This arises from the fact that if we have binary tree with n leaves, In that case, the height of the tree is order log n. So, from this fact you can easily verify that the Merkle branch required to prove the existence of a transaction in a block has size O of log n. So, that is left as a simple exercise. In contrast, if the other scheme that we discussed, that is just concatenating all the transactions and computing the hash value, if h of t0, t1 up to tn minus 1, that is the concatenation of all these, were included in the block header instead of the hash Merkle root field, then what data would be required to prove the existence of a transaction in the block? Now, h of the concatenation of t0, t1 up to tn minus 1 is included in the block header, and an SPV node Bob has only t1. So, what other information should we provide to Bob to convince him that t1 is included in the data that is used to compute this hash? So, we have to present all the transactions t0, t2 up to tn minus 1. So, all these transactions would have to be specified. So, then Bob can put them together along with t1 and verify that the hash is indeed the value that is there in the block header. So, hence the required size would be the size of the list of all transactions, and that is O of n, since there are n transactions. So, log n is much smaller than n. Hence, when a Merkle tree is used, the amount of information that needs to be provided to an SPV node is much lower than in the case where the hash of the concatenation of all the transactions were stored in the block header. So, we have discussed this property that a Merkle tree enables efficient membership proofs of transactions within a block. So, that is the reason for using a Merkle tree as opposed to just concatenating all the transactions and putting the hash in the block header. So, in summary, we discussed various features of Bitcoin. In particular, we focused on the block header and discussed the various fields that are there in the block header. Some of them are integer fields, others are cryptographic hash values. We discussed hash previous block and hash Merkle root, and we discussed the use of a Merkle tree for membership proofs. We will continue our discussion of Bitcoin in the next lecture. Thank you.